Okay, so in this video, we're going to start learning about the idea of torque and how it applies to Newton's second law for rotation. So let's first start with looking at what Newton's second law looks like with rotation. So if we recall Newton's second law, when we were in linear world, then we had that the sum of forces was equal to the mass times the acceleration, so that the net force acting on an object caused that object's acceleration. Now, we have to be specific about what we mean in terms of our acceleration. So the net force acting on the object will equal the mass of the object times the acceleration of the center of mass. So this is now the acceleration of the center of mass of the object. So that is our previous statement of Newton's second law. Just clarified that this is now the acceleration of the motion of the center of mass, not of the, any particular point on the object, but just the center of mass. So for rotation, again, we're going to look at the analogous equation in rotational world to our linear terms. And so instead of a force, to make something have a linear acceleration, we give it a force. To have it have an angular acceleration, we're going to apply what's called a torque. So we use tau, lowercase tau, for torque, and that's defined as torque. And so we can then say that the net torque is going to be equal to not the linear inertia, but the rotational inertia, the moment of inertia of an object, times its angular acceleration. So a net torque causes an angular acceleration. And we've already looked at the idea of moment of inertia, which basically means that something that has a larger moment of inertia then needs a larger net torque to give it the same angular acceleration. So in words, we can basically say that this says the net torque causes an angular acceleration. And that's going to be Newton's second law with rotation. So we've discussed angular acceleration and we've discussed moment of inertia, and now we need to focus on torque. So let's talk now and move on to understanding and finding torque. So torque tau, if we imagine our everyday experiences with making something rotate. If I want to make this pen rotate, well, let's say that it's pivoted right here so that it's able to rotate this way. Well, if I apply a force, I have to apply a force, but how I apply that force matters. So there's a couple things that we know naturally. We know that I can't apply the force, this way in order to make it spin. Instead, the direction in which I apply the force matters. In fact, we know that we have to push on this fairly perpendicularly, right? To the object in order to cause it to rotate. Also, we do know that the larger force I apply, then the more angular acceleration it'll have. But we also know that, notice I'm pushing over here to make this spin. When we open a door, right, we know we don't push near the hinge. So we know that somehow the torque depends, how easily it is to get this thing to spin, depends on where the force is applied, further from the hinge, how the force is applied, perpendicularly, and then of course the magnitude of the force. So let's write down these everyday observations and then look at the equation that matches them. So first, the torque is going to depend on the magnitude, so it depends on the magnitude of the force applied. A larger force would be a larger torque. But it's not just that, it also depends on the direction the force is applied. Right? So that we want to apply the force in a way that makes something spin and not in a way that doesn't. And it also depends on where the force is applied relative to the pivot point. So that's what we know about making things rotate, say doors or wheels. And there's a specific equation that actually takes into account all of these, and it involves the torque product. So I'm going to write down the equation for torque. So torque tau is going to be equal to what we call R, I call that a lever arm, cross F, which is a force. So I'll box that, and then we're going to talk about each term here. So to understand this, let's look at a diagram of, say, something like the pen I was trying to rotate, or a top view of a door that might be pivoted at one end. So we'll draw our pivot. And then let's imagine that I'm applying a force. And in this case, I'm going to draw a force at an angle. So let's say I'm applying a force at some angle that's not exactly perpendicular, and it makes some angle theta with the object. And so I can draw here this right triangle involving the force applied and the angle theta. And so we actually can tell from our intuition that it's actually going to be the component of the force that's perpendicular to the bar that would cause it to rotate. Any parallel components, right, don't cause something to rotate. So that's one of the reasons that that angle is going to matter. So the other thing here that we'll note is when I write this equation that x is not a standard multiplication symbol. Instead, it is a cross product, which is a way of multiplying vectors. So first, if we look at this, this is going to be our torque. The R here is what we call a lever arm. So this is a lever arm. And it basically is the vector that points from the pivot to where the force is applied. So in this case, it would be a vector that points from the pivot to where the force is applied. So let's draw that lever arm in. That's my lever arm R. The force is obviously the force, and then this cross product is very important. It's going to be the way that we multiply vectors that results in us caring about our perpendicular components. If you remember the dot product that we used for work, that took parallel components. The cross product is going to take perpendicular components. The cross product is also known as the vector product because it actually results in a vector. So you multiply your two vectors and you still end up with a vector. And for now, I want to just say that it takes the perpendicular components into account. So in this case, for example, we could say that it would take the component of the force perpendicular to R multiplied by R. So there's going to be then this one equation that satisfies all of our requirements, which is that the torque depends on the magnitude of the force. The bigger the force, then the larger the torque. Depends on the direction the force is applied. We'll analyze the cross product on the next page in a little bit more detail, but that's what this cross product does. It takes perpendicular components into account, and it depends on where the force is applied relative to the pivot, and that is this lever arm. So let's look at this equation in a little bit more detail. So we can write here, we can write it again, that our torque is equal, our torque vector is equal to the magnitude of R times the times the vector R times the vector F using the cross product. So we can write out here the magnitude of the torque can be found by using the fact that the cross product takes parallel components. So the cross product would take parallel components, and so torque is going to then be equal to the magnitude of R times the magnitude of F times the sine of the angle between them, where F sine theta is the component of F that was perpendicular to our lever arm R. So to just quickly redraw our diagram, we had R was our lever arm, F was our force, and then theta is the angle between R and F. And so F sine theta is the component of force perpendicular to our lever arm. And so therefore that is one main way in which we can find the torque magnitude. Now, in general, that gives us the magnitude, but we also need to be able to get the direction of the torque. So if we do this method, we have to be able to get the direction of the torque, or in this case, I'll say, or any cross product. Because cross products show up in the second semester of this course as well, and so they're very important to understand. So to get the direction of the torque, or any cross product, then what we'll do is we're going to use the right-hand rule for cross products. That's what I call it, and because I like descriptive names. And so if we look at this, and I'll make it general so that it applies to any two vectors, and I'll draw a vector A straight up, and then a vector B at a downward angle. And if I want to take, say, vector A crossed into vector B, well, the first thing to know about the cross product is it results in a vector that's going to be perpendicular to the plane that the vectors lie in. So that this is a three-dimensional visualization that you'll do, where whatever your two vectors are, whether it's your lever arm and your force, in this case R and F, or A and B, they all lie in the plane of this paper. So when I take the cross product of them, then I'm going to end up with a vector that's either into or out of the page, perpendicular to the page. So to try to figure out whether it's into or out of the page, I'll demonstrate the method first, and then I'll write it out in words. So what you do is you use your right hand, hence the name right-hand rule, and you shape it like an L, and then you're going to line it up so that your palm faces towards the vector, the second vector, and your fingers line up along the first one. So I would line them like this so that my fingers line up along A, and then my palm faces towards B, so I could go A cross B, A cross B, and then I would end up with my thumb pointing into the page, and so that lets me know that A cross B is into the page. Note that if I decided to try to line my hand up like this, so that my fingers line up along A, it would be very difficult to turn my hand into B, and I'd have to use like my elbow and my shoulders, and it's very uncomfortable, so that's wrong. So you need to make sure that you line it up so that you have less than 180-degree rotation to go from A to B, and that gives you the direction of A cross B. So let's summarize that very quickly. You're going to just put your hand flat with your thumb out. You're going to point your fingers along the first vector, A, so you can rotate them easily to line up with B. So less than 180 degrees is what I mean by that. So this motion versus this. So the direction of your thumb at the end of that is the direction of A cross B. So in our example before, for the torque up here, if I have R and F, so if I'm just going to then look at my R and my F, so let's draw an example here where I have a vector R, and then you can pick vector F up and move it so that it's easier to visualize which way I need to line my hand up in order to make my palm face vector F. So R cross F, that would be out of the page. So in this case, note that the order does matter. F cross R would actually be equal to negative R cross F, and that's something that you can try for yourself in order to get comfortable with the cross product. You can just draw vectors on your page, play around with it, and try to make sure that you understand that A cross B is negative B cross A. Okay, so that's our general way for finding torque, which is very often that you're given some lever arm and some force applied, and then you can use the component of the force perpendicular to R, or some way to use RF and turn the sine of the angle between them. And that gives you the magnitude of the torque. And then to get the direction, you can use this method of using the right-hand rule for cross product.